All right, here's the what we're going to do today. Talk about a process that you're already a little bit familiar with, even if you don't know it. Now, you may have done this before a little bit, but not a lot, I bet. Now, we looked at some stuff like this the other day. If I had something like 2x minus 1 times x plus 3, this is that multiplying polynomials assignment. What do I do? Distribute, sure. Okay, so I can take the 2x gets distributed to the x in the 3, and what do I get from those two terms?
2x squared.
Okay. 2x squared plus 6x, good. Now what if I take the negative 1 and I distribute that?
Negative x minus 3.
Negative x minus 3. And I could combine those two terms, couldn't I? Right? And if I do that, I'm going to get...
2x squared plus 5x minus 3.
There you go. I get my final answer, 2x squared plus 5x if I combine the like terms, which are only the x terms, right? X squareds and x's do not add. Some people were trying to do that. X squareds and x's don't add. So there we go. Now this process we called expanding, didn't we? If we start with something like that and we multiply it out, we called that expanding. That's your last assignment. You're going to find that that assignment is pretty easy. It's not that big a deal. Once you get the hang of it, it's very, very simple. Expanding is simple. Now, we're going to talk about the opposite process today, and that's a little trickier. It's not horrible, but it's a little trickier. If we start with a polynomial and we want to go backwards and write it as a product of factors. Yes, sir?
Isn't it 2x minus 1 equals 0? Is that how you do it?
Okay, yeah, you're jumping. You're right. You got good. Hold that thought. I'm going to ask you about that in a second. That's going to be real important information. Okay, so this is what we call factoring, the process of taking a polynomial and breaking it apart into a product of factors, and that's what we're going to work on today a little bit. Okay. Now here's where this. Why do we do this? I think it's important in math sometimes to talk about why do we learn these skills, what are they useful for. I mean, it's like in a sport, you do lots of, in practice you're going to do different kinds of drills, and they may not look like a game situation, but you're always doing it for a reason. You're doing it to emphasize or to strengthen a skill that's going to be important in a game situation. Well, what's the game situation here? The game situation is this, solving problems like this. Okay. Now, we'll come back to that. Let's just briefly kind of get up to speed and warm up a little bit with a problem like we've done in the past already. What if we had something like this? 3x plus 5 equals x minus 7. I want you to solve for x. What do I do? Okay, get the x's on one side. Good. Which side am I going to put them on? Left side, where I have the most of them to begin with. So how do I do that? Subtract x. Okay, so that's going to give me what? 2x plus 5 equals negative 7. And now this is good, right? Now we can, remember what we always say, if we can point to a single x, what can we do? If we can point at a single x in an equation, we can what? Isolate it, sure. Right? By reversing order of operations. So what are the two steps we would go through to isolate x? Good. Subtract 5 and divide by 2. And if we do both those things, just do this in your head. What do you get? Negative 6. Very good. Okay, easy enough, right? No big deal. You guys are getting very good at that stuff. Okay, but what's the problem here?
You have an x squared.
Oh yeah, there's an x squared. So I'm sunk. I can't do that last trick. It will not work. I can't combine like terms here, right? I'm stuck with x squareds and x's, and so I can't isolate a single variable because I can't get I'm always going to have two different ones, right? Those terms will not combine. So to solve an equation like this, we have to do something completely different. And this, by the way, is called a quadratic equation. Now, the fact that it's set equal to 0 is going to be important. But what if it hadn't started off being equal to 0? What if it had said equals 18? I could have just subtracted the 18 to this side and made it equal 0, right? Turns out that's going to be an important thing. So the fact that it's equal to 0 means it's in what we call standard form in algebra. And we'll talk a lot more about that next year. Yes, ma'am? Yes, you may. You bet. Okay, so I'm gonna part ways here with this equation for a little bit, and we'll come back to it. Here's what I want to do. Let's take a look at. Oops. I don't know if this PowerPoint's going to work. It didn't seem to work well last period, but we'll try it. No, it's not going to work. I'm not even going to bother with it. I'm just going to bail on it. We don't need it. Okay, so how do we factor these things? Now we're going to do quadratic trinomials. Yes, ma'am. Oh, go for it. Okay. If we've got these quadratic trinomials, 3 terms, they're always going to have this form. The ones that we're going to look at are going to always have this form. X squared plus bx plus c, where b and c are just numbers. Okay, it could be positive, could be negative. So let's look at all the different cases we could where, b is positive, c is positive, maybe b is negative, c is positive, etc. I'm going to give you an example here. Let's take x squared plus 12x plus 35. Now, if I want to factor this, I want to break it apart into a product of 2 factors, I can already start with my template there. Okay, I know it's going to look something like that. Factoring is like unexpanding or unfoiling, right? So what do you suppose the first term of each factor has to be? It's going to have to be x, isn't it? Because if I were to reverse this process and distribute that x to this polynomial, x times x is going to give me x squared. I need those to be x's to get my x squared when I multiply them out, right? But the question is, hey, don't be throwing stuff. If I want this thing to work, I need to know what the numbers are going to be, the magic numbers. What do they have to do? Do you remember this from last year? What do the 2 numbers need to do in order to expand to give me that? They have to multiply to something and add something. You remember this? Good. They have to add to b and multiply to c. They always have to multiply to the constant and add to the number, the coefficient of x, the number that's being multiplied by x. Okay, so we need to know what those numbers are. Now, we can get a head start on this, though. By knowing the signs of the numbers, that's helpful. If the 2 numbers multiply to a positive number, what does that tell you about their signs? They're both positive, or they actually could also be both negative. But in this case, if they're going to multiply to a positive, so they're the same sign, and add to a positive, what must they be? Positive. Okay, so then we can put the signs of the numbers right there. They're both positive. Well, what would they be? Anybody know? 7 and 5. There you go. Okay. And how could we check to see if we did it right? Yeah, we could distribute this out or FOIL it out and see, right? And it would work. We got it. Okay, let's try another one. Okay? So we can go ahead and write our template there. That much we know before we even start to think about it. Now, what about the signs of the numbers this time? Okay, one's negative and one's positive because they multiply to a negative. Now, which one is bigger of the 2? And why? they multiply to negative 40 and add to positive 3, which number is bigger, the positive number or the negative number? Positive. How come the positive?
Because the negative
If the negative number were bigger, they would add together to be negative. When I add a negative number and a positive number, don't they partially cancel? Right? Well, whichever one is bigger to start with has a little bit left over. So the positive must have been bigger because we've got 3 left over, positive 3 left over when we combine those two and they cancel, right? Okay, so what I like to do then, and you don't have to do it this way, but I think it's a good habit. Let's put the bigger one first and the smaller one second. So we know the bigger number is positive. In fact, how much bigger is the positive one? If they cancel all except for that positive 3, how much bigger was the positive number? What do you think, Neil? They are, right. They're positive 8 and negative 5. And we know right away that the positive number must be 3 bigger, because after the negative number was totally canceled, that's how much positive was left over. Right? That's kind of useful to know that we can look for numbers that are fairly close together. Right? So 8 and 5. Make sense? Now I know you're probably thinking, man, this is okay, I got it. But these techniques are important because what if the numbers I was choosing weren't 8 and 5? What if they were something like, 3-digit numbers? Then it gets a lot harder to do, right? And then being very strategic and kind of looking for the patterns gets to be very helpful. I'm not going to look at any of those today, but we will at some point. Okay, what about this one? Oops. Messed it up. No, I don't want to do that one. That one wouldn't work. Okay, what about the signs this time?
-9 and 3.
Okay, negative and positive, right? The negative one is bigger. We'll put that first. Negative 9 and 3.
It's positive.
Right? That make sense?
Positive.
Oh, whoops, positive. You're right. Okay? And then last one, at least we'll do one more. How about okay, make it a little tougher, huh? What can you tell me about the two signs this time? Okay, if you're going to multiply to a positive, that tells me they're the same sign, right? So they both must be negative if they're adding to a negative. Now, what two numbers multiply 68 and add to 21? Trying to challenge you a little bit. These are getting too easy. How can I find out?
Can't you just divide?
Can't divide them. Because remember, I'm trying to find numbers that multiply to 68 and add to 21, but they're both negative, right? So I don't want to just try random numbers. I want to only try certain pairs of numbers. How could I whittle this down a little bit? If I know the numbers multiply to 68, is that helpful? Yeah. It is, isn't it? I can just find factors of 68, right? Now how do we do that? Let's practice that. If I want to find factors of 68 that are negative, let's just start with the easiest obvious ones, like 68 and 1. Now, do those add to negative 21? No. No, those add to, what do those add to? Yeah, let's keep track of this because there's a trend we want to see here. So what's the next one I could choose?
34.
Okay, good. Now look what I'm going to do. I'm going to divide this by 2 and multiply that by 2, right? So I get negative 34 and negative 2. Well, those add to what? Negative 36, still too big. Okay, what do you think?
7 and 14.
Okay, it's gonna be 7 and 14, isn't it? But let's keep going with this and see if we can see a trend though. That is gonna be the answer. 3 doesn't go into 68, does it? Because 6 plus 8 is 14, not divisible by 3. But if I cut this in half, well actually there we go, no. Negative 17 And that's it, isn't it? Right? Those add to negative 21. Good job, Jimmy. Right? Everybody see that? Okay, and could I go any further? I don't think I can. But what do you notice here? I want you to notice this trend. As the two numbers that multiply to 68 are very far apart, look how big the sum is. I get big numbers. But as the two numbers draw closer together, the sum gets a lot smaller, doesn't it? Okay, that's always true. That's a good thing to recognize. Yes, ma'am. Did I make a mistake? You sure?
Yeah, 14.
No, I think it is 17 and 4, isn't
Yeah,
it?
it is.
Yeah. Yeah.
58.
Yeah, because 17 times 4, yeah, that is 68. Now, I probably picked a bad example because there weren't any other factors, but if I had picked a little better example, we would have seen that as these numbers get closer and closer, they add to smaller numbers. Okay, so that gives you a little hint. If this number in here is really small, what does that tell you about the two numbers, the two factors that multiply together? That, yeah, they're going to be close together, right? The smaller it is, the closer together the two numbers are. Okay? All right. So that's a good start. Now, why did we do this? Why is that so helpful? Okay, well, let's, before we move on, we got to do a little warm-up exercise here. I feel like our mental math we need to strengthen that a little bit. So everybody, don't write, don't use your calculator. Just try to do this in your head for me, please. Keep track. So start off with 2. Okay, times 4. Okay, don't say it out loud, just do it in your head. Times 5. Okay, so 2 times 4 times 5, keep track, times 17.315. Okay, you got it? Times, oh, come on now, you can do this, can't you? I promise you, I'm going to get the exact answer with this. That's how good I am, I'll show you.
You lost me.
What was that?
Hang on, we'll keep going. So those of you that are still going, I'll make one up for times. 1,997,427.538.
We got it right now.
Okay, so we got that, okay. Times pi, okay, times 0 equals, oh, so that'd be pretty easy, didn't it? Okay. So I got it. Okay, now, moral of the story being that if I multiply times 0, what do I always get for an answer? 0. In fact, if I multiply numbers together and the answer is 0, what do you know had to have happened? I had to have multiplied by 0 in there somewhere, right? Had to. It's the only way to get 0 for an answer. That's huge. That's huge. In fact, this is such a big deal in math that we actually give it its own name. We call this the zero product property. And this is the big trick that allows us to solve this equation. Okay, now, what can we do here? If there were a way, we can't find this answer just by guess and check. I mean, just by randomly picking values of x, we could be here forever trying values that might never work because maybe there isn't even a solution, right? So we can't do this problem without somehow being tricky, right? Here's our trick. Can we factor this thing? Yeah. We just practiced that. We're pretty good at it, in fact. What are the two numbers that multiply to negative 18 and add to negative 3? Negative 6 and positive 3. Okay, now watch very closely. If you watch this closely, this is huge. You'll get this and you'll have it forever. So you can do this a lot next year. Okay. Now, what's the only way that this times this can equal 0? Okay, yeah, if one of them is equal to 0. So forget about the x's and the 6's and the 3's. All we're thinking right now is left hand and right hand. I've got some stuff behind my left hand and some stuff behind my right hand, and I'm multiplying those two things. I've got the product of left hand and right hand. In order for the product to be 0, wouldn't you agree that either my left hand has to hide a 0 or my right hand has to hide a 0, right? So all we have to do to find out the values of x that could make this true is answer two very simple questions. What are the values of x that could make my left hand hide a 0 or my right hand hide a 0? Easy, right? Very easy. Let's take the left hand case. all we need to know here is what values of x make x minus 6, because that's what's behind my left hand, make that equal 0. What is it? 6. Okay, there's the left-hand case. That's the number, the value of x that made my left hand 0. What about the right hand?
-3.
Yeah, here we got x plus 3 needs to equal 0. So x equals -3. So those, how about that? Those are the two solutions. Isn't that cool? That's the zero product property. If we can take some big ugly quadratic equation like this, as long as it's set equal to 0, if we can factor it into a product of factors, then all we have to do is set the factors equal to 0, right? And then we get the solutions. That's a great trick. Lots of good tricks in math. All right, make sense? Okay,